In this video, we're going to talk about subsets and power sets, and I'm going to represent subsets visually first. If A is a subset of B, then every element in A must also be in B. Visually, this means that A must be contained within B. And we would write this, A is a subset of B. Now, it can also be the case that A is exactly the same as B. So if we have A and B the same size, this is also a subset, and you can see this by the little line underneath. If we have the subset symbol with a line underneath, that means subset, which means it can be smaller or equivalent, or contained or equivalent. But if we have something like a proper subset B without the little bar at the bottom, this means that A must be strictly smaller than B. Let's do some examples. So these are just true or false questions. I'm asking, is the set containing ABAA a subset of the set containing ABC? The first thing we have to remember is that repeated elements do not matter, so we can remove the remaining A's. So now we're asking, is AB a subset of ABC? Well, we have to check, is everything in A here also in B? So we take a look at A, we say, okay, is A in B? The answer is yes. Okay, that's good. What about B? Is B in the second set? Yes, it is. That's good. Therefore, the set AB is a subset of ABC. So this would be true. And we could even draw this. We could do one, I shouldn't use numbers, we should use A, B, and C. And we can circle them, right? We can say, okay, AB is A, and then we can circle A, B, and C, which is B, and we'll notice that A is contained in B, therefore A is a subset of B. You can do it visually, or you can just do it by definition. So what about CD? Is CD a subset of CD? And the answer is yes, that is true. And that's because every element in our set A here is a member of the set B. So C is in A, therefore C is in B. D is in A, therefore D is in B. Now, what about the next one? Well, the next one, I'm asking, is the set containing A a subset of the set containing the set containing A? That was a very difficult sentence to say. Essentially what I'm asking, is this element A in our second set? And the answer here is no. So if I were to list out all the elements, really I have A on the left, and on the right I have the set containing A. Now, A, little a, is in our set A, while the set containing A is in B. So we can see A is not in B. A is not a subset of B. We don't see A anywhere in B. We just see the set containing A. Okay, so no, this is false. This is not the case. So what we could say is we just stick a line through it, and that means that is not a subset. Okay, finally, the empty set. Is the empty set a subset of XYZ? The answer is yes, it is true. The empty set is a subset of every set, because the definition says everything in here must be in here. Well, there is nothing in the empty set. Therefore, this is trivially true. The empty set is a subset of every single set. Okay, so now that we have a kind of a rough idea of what subsets are, we can now talk about power sets. So the power set of A, with this little p, A, is the set containing all possible subsets of A. And this can be a little bit of a confusing concept to wrap your head around first. Let's figure out how to generate all possible subsets first. This is how I like to think of it. With every element in the original set A, we start with an empty set, and we ask ourselves, do we add the first element? So here I'm starting with the empty set, and I'm asking myself, should I add A? If I add A, then I get the set containing A. If I don't add A, I'm left with the empty set. Now we move to the next element, and we ask ourselves, should we add B? If the answer is yes, then we end up with the set A and B. If we don't, then we end up with the set containing A. Over on the empty set side, we can ask ourselves the same question. Should we add B? If yes, then we have the set containing B. If no, then we have the empty set. And now each of these is a possible subset of the set containing A and B. So if we have 10 elements in our original set, then we have to ask ourselves yes or no 10 times, which means there's going to be 2 to the 10 possible subsets. So this tree doesn't really work when you get more and more elements, because it's just more and more writing, and it's really impossible at that point, and even super tedious to write it out. Now, these are all the possible subsets. The power set is the set containing all of that. So this would be the set containing the empty set, the set containing A, the set containing B, and the set containing A and B. And those are all in the same set. Another way of doing this would be to say, okay, the power set, I can have no elements, so I can have the empty set. I could have a set with just one of the elements, so A and B. I could have a bunch of subsets with all the pairs of elements, A and B, so on and so forth. Now, really, talking about counting, the reason why I showed you that tree was so we can talk about the size of the set. So if your original set A has n elements, then the power set, the size of the power set, will have 2 to the size of A, or 2 to the n. And this might sound a little bit confusing at first, but really, for each element, we're either adding it to a subset or we're not. So there's 2 choices per element. So we can see before, imagine if our subset, or original set A, just had no elements in it. Then we could have 2 to the 0, which is one possible subset. That would be the empty set. If there was just A, we'd be asking ourselves, do we add A or not A? Then we'd have 2 to the 1 equals 2 possible subsets. With 2 elements here, we see that there are 2 to the 2 equals 4 possible subsets. So let's say I have that A has 6 elements in it. Then the cardinality of the power set of A would have 2 to the size of A, which is just 2 to the 6, which should be, I think, 32. 2, 4, 8, 16, 32. Should be 64 possible subsets. And that's quite a bit of subsets. That's quite a lot of possible subsets. You would never be asked to write the power set of something this large on an exam. In fact, 2 to the 3 is probably the highest you would go writing it out by hand, or maybe 2 to the 4 if your professor is a little bit sadistic. But I hope this intuitively describes why the power set grows like this in powers of 2. It's because for each element you have a choice of putting it in or not. So now that we've covered power sets with simple examples, of course, if you're a little bit confused, post comments, rewatch the video, write it out by hand, try to follow along. We're going to cover some of these tricky questions. The first one, of course, is the power set of the empty set. Okay, the power set of the empty set. What? Okay, well, remember that the empty set is essentially size 0. So the size of the empty set is equal to 0. This means the size of the power set of the empty set should be 2 to the 0 equals 1. So we should have one element in there. And here's a cool thing to remember. The empty set is an element of every single power set. So the power set of the empty set is just the set containing the empty set. So there's a set containing no elements inside the power set. Again, another way to write this would be just the set containing the set with nothing. So if you don't like the 0 with a line through it, you can just remember this as the set containing nothing in it. Okay, what if I have the power set of the set containing the empty set? Okay, now this is a little bit more confusing, but if we remember that, okay, the set containing the empty set, the size of this is 1. So the power set of the set containing the empty set should have 2 to the 1 equals 2 elements in it. So the first one would just be the empty set, because the empty set is an element of every power set. And then you'll also have the set containing the empty set as an element. Okay, now this might be a little bit hard to wrap your head around, but remember, if we just draw our tree for this, we can just draw the tree the same way we did it before. We can start with the empty set. If we don't add the empty set in, we're just left with the empty set. If we add the empty set in, then we have the set containing the empty set. So therefore, the power set is just going to be these two possible subsets in a set. So again, this is how we can figure out these tricky situations without being confused by the notation here. Now, two more theoretical questions. Is A a subset of the power set of A for any A? Well, let's look. This here, in this example, is A. And here we have A. So we see that A is an element, but does this hold for every single set? And is A a subset of the power set of A for any A? The answer is no, it's not a subset, but it is an element. Now, let's think about this. Well, let's go back to this example. Here is A. A is the set containing A and B. If we add all of our elements, we get the possible subset, which is itself. So we get A back as a possible subset. But remember that these subsets are elements of the power set. So whatever your original set is, it will be an element of the power set. There are some cases where the original set is a subset of the power set, but not all cases. For instance, the set AB is not a subset of the power set, it's just an element in this case. But if we compare it to this example, we would see that A is a subset of the power set. But this is just one situation in which it does occur. So, all the time A is an element of the power set, but not all the time is A a subset of the power set. Okay, so let's just do some exercises. I'm not looking forward to the second one, but we can do the first, second, and third. The first one says, let C, the size of C, equal K, and the size of D equal J. What is the size of the power set of C cross D? Okay, well, let's remember. The size of C cross D is just the same thing as the size of C times the size of D, so this is just K times J. Okay, which means that the size of the power set of C cross D will just be 2 to the size of C cross D, which we know is just equal to 2 to the K times J. So when you take Cartesian products with power sets, things get really crazy really fast. The second one asks, list the elements of the power set of the empty set. Well, we do this step by step. So the power set of the empty set is just the set containing the empty set. So now we want the power set of the set containing the empty set, and again, we've done this before. This is just the set containing the empty set as well as the set containing the empty set. Okay. So we can take power sets of power sets. And once again, it becomes a pain really quickly to write out. The final one is more theoretical. So if the size of A is equal to M, what is the size of the power set of the power set of the power set of A? Well, we can take this step by step. So the size of the power set, in fact, I'm not going to write this out again. This is just going to be equal to 2 to the size of the power set of A. Okay, and this is just equal to 2 to the 2 to the power set of A, which is just equal to 2 to the 2 to the 2 of the size of A, which of course is equal to 2 to the 2 to the 2 to the M. So once again, your professor, if he's really sadistic, could just ask you about the cardinality of the power set of the power set of the power set of the power set of some set, and ask you for the size. So that is subsets and power sets. If you have any questions, please leave them in the comments below and I will do my best to answer them.